sir, and my dear friends. Today I am going to present my topic context switching, how operating system switches between processes. Before starting the presentation, let me ask you a simple question. Suppose you are working on Microsoft Word, listening to song on Spotify, downloading a file in Google Chrome and chatting on WhatsApp all at the same time. Have you ever wondered how your computer manages all these applications simultaneously, even so your computer has only one CPU core or a limited number of CPU cores? How does the processor decide which application should run fast and which one should wait? Does one application stop completely while another runs? The answer to all these questions lies in a very important concept of operating system called context switching. Context switching is one of the core functions of process management. It allows the CPU to switch from one running process to another so quickly that user feel all application and are running at the same time. In today's presentation, I will explain what a process is, why context switching is required, and how it works step by step. What role the process control block or PCB plays, how the CPU scheduler and dispatcher work together, and finally the advantage, disadvantage, and real life application of context switching. By the end of the presentation, you will clearly understand how modern operating systems like Windows, Linux, Android, and Mac efficiently manage multiple running processes. So, without taking much time, let's begin by understanding what a process actually is. So, we can move to the next slide. Introduction to process management. Before understanding context switching, we first to need to understand what a process is. In simple word, a process is a program that is currently running or executing. Whenever we install software on our computers such as Google Chrome, Microsoft Word, VLC Media Player, or Adobe Photoshop, these are simply programs sorted on a hard disk. They become processes when only we open and execute them. For example, when you double click Microsoft Word, the operating system loads the program into memory and start executing it. At that moment, Microsoft Word become a process. A process is much more than just program code. It contains the program instruction, allocated memory, CPU register, open file, input output resources, and another information required to execute successfully. Now let's understand why process management is important. Modern computers rarely run only one application. Imagine you are attending an online classes at the same time Google Meet is running. You are taking notes in Microsoft Word. Chrome is downloading a PDF. Spotify is playing music in the background. All these applications are separate processes. The operating system must manage all of them efficiently. This responsibility is called process management. The operating system performs several important tasks under process management. It creates new processes whenever applications are started. It schedules CPU time among different processes. It synchronizes processes whenever they need to communicate. It terminates processes when they finish execution. Importantly, it ensures that one process cannot interfere with another process. Without process management, applications would conflict with each other, causing system crashes and poor performance. Therefore, process management forms the foundation of multitasking operation system. Now that we understand what a process is, let's move to our next topic, context switching. So we can move to the next slide. What is context switching? Now we come to the main concept of today's presentation. What is context switching? In simple word, context switching is the process in which the operation system temporarily stops one running process, save its currently state, and its start executing another process. You may wonder why this is necessary. The answer is very simple. The CPU can execute only one instruction at a particular instant of a single core. However, user expect many applications to work simultaneously. To create this illusion, operating system rapidly switches the CPU from one process to another. This switches happens within a few milliseconds. Because the switching is extremely fast, user feel that all applications are running simultaneously. Now let's understand the meaning of the word context. The context of a process means all the information required to resume the process later after exactly the same point. This include the value of CPU register, the program counter, the stack pointer, process states, and other execution details. Suppose you are typing an assignment in Microsoft Word, suddenly you are switched to Google Chrome. to search for information. After 2 minutes, you return to Microsoft Word. You notice that your cursor is exactly at the same position where you left it. How is this possible? The operating system saved Word context before switching it to Chrome. When you come back, it restored the saved context. This is exactly what context switching does. Context switching is extremely important in multitasking operating system. It ensures that every process gets a fair opportunity to use the CPU. It prevents the uh, one application from occupying the CPU continuously. It also improves system responsiveness because the interactive application receives CPU time quickly. Without context switching, multitasking would not be possible. We would have to close one application completely before opening another one. Modern computer systems such as Windows, Linux, Android, and Mac all really heavily on context switching to provide a smooth user application. So now that we understand what context switching is, the next question is what exactly is saved during a context switch? To answer that, let's move to the next slide to understand what the answer of this question. So we can move to the next slide. What is process context? In simple word, process context is the complete information about a process that is required to stop it temporarily and later resume it exactly from the same point where it was interrupted. Let us understand this within a real life example. Imagine that you are writing an assignment in Microsoft Word. You are already completed 5 pages and currently typing the sixth page. Suddenly, your friend sends you an important message on WhatsApp, so you minimize Microsoft Word and open WhatsApp to reply. After a few seconds, you come back to Microsoft Word. Have you noticed that your document open exactly where you left it? The cursor is still at the same position, the unsaved text is still there, and you can continue typing without any problem. How is this possible? Any idea? It happened because the operating system saved the entire context of Microsoft Word before switching to WhatsApp. When you return, it will restore that saved context, allowing Word to continue from the exact same point. Similarly, when the CPU switches from one process to another, it's first save the context of the currently running process. Now let's understand what information it is included in the process context. The first component is the program counter, also called the instruction counter. The program counter stores the address of the next instruction that CPU has to execute. Suppose the program has completed 150 instruction and the next instruction is number 151. The program counter remember the information when the program resume execution start directly from instruction number 151 instead of starting from the beginning. The second component is the CPU register. Register are very small and extremely fast storage location inside the CPU. So the temporarily store important data in intermediate calculation, memory address and instruction currently being processed. Before switching to another process, the operating system save all these registered value so that notify is lost. The third component is the stack pointer. The stack pointer keep track of function call local variable and return addresses. For example, if a process executing a function and gets interrupted and the stack pointer remember where the function was, so that execution can continue correctly after the process resume. The fourth component is the process state. Every process can be a different states such as running, ready or waiting. The operating system store the current state, so it is now what should happen, what the process selected again. In additional to these, the context may also include scheduling information, memory management information and input output status. Without saving all this information, the operating system would never know where the process is stopped. Every time a process is resumed, it would have to start from the beginning. This would waste a lot of time and making multitasking impossible. Therefore, process context act like a checkpoint of the process. It stores everything necessary so that execution can continue smoothly after a context switch. Now that we know what information is saved, the next question is why does the operating system need to perform context switching frequently? Let's understand in the next slide. So we can move to the next slide to understand the process. scheduling context. Need for context switching. Now let's understand why context switching is needed. At first glance, it was seen unnecessary. It repeatedly stopped one process and stopped another. However, without context switching, modern computers should not be able to perform multitasking. The biggest reason of context switching is multitasking. Today, almost every computer user run multiple applications simultaneously. For example, imagine that you are attending an online lecture for Google Meet. At the same time, you are making notes in Microsoft Word. Meanwhile, Google Chrome is downloading a PDF in the background. You are also listening to music on Spotify. These are four different processes running together. You can idea how these processes can work simultaneously. Now, suppose your computer has only one CPU core. Can that CPU execute all four processes at exactly at the same instant? The answer is no. The single CPU core can execute only one instruction at a time. So, how does it appear that all four applications are running together? The operating system gave each process a very small amount of CPU time called a time slice on time quantum. After one process uses its allotted time, the operating system perform a context switch and allow another process to use the CPU. Since the switching happens thousands of times, every second user feel that all applications are running simultaneously. The second reason is better CPU utilization. Sometimes a process needs to perform input-output operation. For example, while downloading a file, the browsing has to wait for data from the internet. During the waiting period, if the CPU simply waited, it would remain idle, which is wasted for processing power. Instead, the operating system switches to another ready process. This ensures that CPU remains busy and overall system perform improve. Another important reason is system responsiveness. Suppose you are editing a document and suddenly click the start menu. If the operating system waited for every running process to finish before opening the start menu, the computer would feel very slow. Instead, it immediately perform a context switching so that the start menu appear almost instantly. This improves the user experience. Context switching also help in fair CPU sharing. Every process get an opportunity to execute. No single process can occupy the CPU forever. This is especially important in multi-user system where many users may be running applications simultaneously. Finally, context switching supports real-time system. Certain applications such as medical device, air traffic control system, and industrial automation require immediate CPU attention. The operating system quickly switches to the CPU for this high priority process whenever necessary. Therefore, context switching is not just a changing process. It improves multitasking, CPU efficiency, fairness, responsiveness, and overall system performance. Now we know why context switching is necessary. The next question is, what exactly does a context switch happen? Let's understand that is that in the next slide. So we can move to the next slide. The next slide is, what does context switching occurs? So we can move to the next slide. What does context switching occurs? Now let's discuss when context switching actually take place. The operating system does not perform a context switch randomly. It happens only under specific situation. The first situation is time quantum expiry. In multitasking operating system, every process receive a fixed amount of CPU time called a time quantum. For example, suppose each process receive 20 milliseconds. Once those 20 milliseconds are over, the operating system immediately save the current process and switches to another ready process. That this ensures that every application gets a fair chance to execute. The system situation is input-output request. Sometimes a process need to wait for an external device. For example, a browser may wait for internal data or a program may wait for a file to be ready for the hard disk instead of waiting CPU time. The operating system perform a context switch and start executing another process until the first one become ready again. The third situation is process completion. When a process finishes all its tasks, it enters the terminate state. Since there is nothing left to execute, the operating system simply selects another process from the ready queue and give it to the CPU. The fourth situation is interrupts. Interrupts are signals that require the CPU immediate attention. For example, pressing a key on a keyboard moving the mouse on receiving network packet can generate interrupts. When an interrupts occur, the operating system may temporarily suspend the current process, handle the input, and then either resume the same process or switching to another one. The fifth situation is higher priority process arrival. Suppose a low priority process is currently using the CPU. Suddenly, a high priority process arrives. In the primitive scheduling system, the operating system immediately saves the low priority process and give the CPU to the high priority process. This ensures that critical tasks are completed without unnecessary delay. Therefore, context switching occurs due to time quantum expiry of waiting process completion, interrupts, and priority scheduling. This event ensures that the CPU is always used efficiently while maintaining fairness and responsiveness. Now, that's we now context switching occurs. Let's move to the next slide and understand the different states through which a process passes through its life cycle. So we can move the next topic. So process state. Now that we now when context switching occurs, let's understand the different states through which every process passes during its life cycle. A process does not remain in the same condition all the time. Depending on what is it is doing, and its state keeps changing. The operation system continuously monitors these states and decides what a context switch is required. The first state is the new state. Whenever we open an application such as Google Chrome, Microsoft Word, the process is first created by the operating system. At this stage, the operating system allocates memory, create the process control block, and prepare the process for execution. This initial stage is called the new state. After creation, the process moves to the ready state. In this process, the process has everything it needs except one thing. The CPU is ready to execute, but it is waiting for the ready queue until the CPU become available. You can compare this as a student waiting outside the examination hall. They are fully prepared to write the exam, but are waiting for permission to enter. When the CPU become available, the process system select one process from the ready queue. The process then enter the running state. In the running state, the CPU is actively executing the instruction of the process at any given moment. Only one process can be the running state on single core processor. However, a process may not always continuous running. Sometimes it needs to perform an input output operation such as reading a file, downloading data, and the internet is waiting for the user input. In that case, the process moves to the waiting state, also called the blocked state. While the process waits from the input output operation to finish, the CPU is free to execute another process. This is one of the major reasons why context switching improves CPU utilization. Once the waiting task is completed, the process return to be ready state, waiting again for its turns to use the CPU. Finally, after completing all these instructions successfully, the process enter the terminate state. At this state, the operating system realizes all the memory and resources used by the process. So the complete cycle is ready, running, waiting, ready, running, terminated. Understanding this process state is very important because context switching mainly occurs while process name between the running, ready, and waiting state. Now they are understanding the process life cycle. The next question is why does the operating system for all the information about this process? The answer is process control block, which we'll study in the next slide. So we can move over the next slide. Process control block, PCB. Now let's discuss one of the most important concept related to the context switching, the process context block, commonly called the PCB. The PCB is basically data structure maintained by the operating system. You can think of it an identity card or record file of a process. Just like every student in a college, such as file containing details such as roll number, name, department, attendance, and marks. Every process has a PCB containing all the information required by the operating system. Whenever a new process is created, the operating system immediately creates its PCB. Its PCB contains several important fields. First is the process ID, PID. Process ID. Every process is assigned a unique identification number. This helps the operating system distinct on process to another, one process to another. The second field is the process state. It stores whether the running is process currently new, ready, running, waiting, or terminated. The third field contains the program counter. This tells the operating system which instructions should be executed next when the process resumes. The fourth field contains the value of the CPU register. Since register contains temporary data registered during execution, their value must be saved before switching to another process. The PCB also stores CPU scheduling information such as process priorities, scheduling algorithm details, and queue information. Another important section is memory management information. This includes detail about memory allocation, page tables, and segment tables used by the process. The PCB also store accounting information such as CPU time used by the process and process owner details. Finally, it contains input-output state information including open files and device currently being used. Why is the PCB so important? Because during context switching, the operating system saves the current process information into its PCB before switching to another process. Without the PCB, the operating system would not know where the process stopped or how to resume it later. In simply word, the PCB acts like a memory of the operating system. It remembers everything about every process so that execution can continue smoothly after a context switch. Now that we know what a PCB is, let's understand its role during a context switching. So we can move the next topic, role of PCB in context switching. Uh, in the previous slide, we learned what a process control block is. Now let's understand how it actually helps during context switching. Suppose process is currently running, suddenly its time quantum expire. The operating system now wants to execute process B. Before switching, the operating system cannot simply stop process because all the current information would be lost. Instead, the operation system perform the following step. First, it saves the program counter, CPU receive registers, stack pointer, process state, and other execution detail of process A into its PCB. This operation takes only a few microseconds, but it is extremely important. Once all the information is safely restored, process moves to the ready to or winning state. Now the operating system selects process B. Next, it reads the PCB of process B. All the previous saved information of process B is copied back into the CPU register. The program counter is restored. The stack pointer is restored. The process state changed to running. Finally, the CPU start executing process B exactly from the point where it was interrupted is earlier. This entire sequence is called context switching. Let's understand this with a simple example. Suppose you are waiting an assignment in Microsoft Word. Suddenly, you receive an important email and switch to Gmail. This operating system saves Word's currently state into its PCB. After reading the mail, you switch back to the Word. The operating system restored Word information from the PCB and you continue typing from exactly the same cursor position. This is exactly how context switching works internally. Therefore, the PCB acts like a storage box that temporarily stores all the important information of a process whenever the CPU switches to another process. Without the PCB, context switching would not be possible because the operating system would lose track of every process. Now let me understand the PCB role. Let's make to the next slide and study the complete step-by-step context switching process from start to finish. So we can move the next slide. So we can start step of context switching. Now that we understand what a process control block is, why it is important, let's study the complete step-by-step process of context switching. This slide explains exactly what happens inside the operating system whenever the CPU switches from another process to. Although the entire process happens within a few milliseconds internally, this is several important steps. Let's understand them one by one. First, a process is running. Initially, suppose a process is running on the CPU. The CPU is executing its instruction one after another. Everything its work normally. Suddenly, one of several events occurs. For example, the process completely its time quantum request an input output operation or a higher priority process arrives. At this time, the operation system decides that it's time to switch the CPU. Step 2. Save the current context. Before stopping process A, the operation system cannot simplify remove it from the CPU. If it did, all the information about process would be lost. Therefore, the operating system saved the completely context process A to process control block. This information saved include program counter, CPU register, stack pointer, process state, scheduling information. You can think that this is a saving progress in a video game. Whenever you save your game before exiting, uh, uh, you can later continue from exactly the same level instead of starting from the beginning. Similarly, the PCB stored complete process from the running process. Step 3. Select the next process. After saving the context, the operation system look into the ready queue. There may be many processes waiting for the CPU time. The CPU scheduler select the next process according to the scheduling algorithm being used. For example, it may use round-robin priority scheduling on first come first serve. Step 4. Restore the new context. Now the operating system loads the PCB of the select process. It stores all previous saved information into the CPU. The program counter tells the CPU which instruction would you execute next. The CPU register are stored. The stack pointer is restored. Everything becomes exactly the same it was before the process was interrupted. Step 5. Resume execution. Finally, the CPU start executing a new process. The user never noticed the switch become it happens extremely quickly. This ensure sequence repeats thousands of times every second. This is why user feel that all applications are running simultaneously, even though only one process is executing on the CPU at the particular instant. So the five major steps are running process, save context, select next process, restore context, resume execution. This is completely context switching cycle. Now let's understand the same process using a flow diagram. So we can move the second slide. Uh, this slide shows the graphical representation of the context switching. Sometimes diagram help us to understand concept of much faster than theory. Let us go through the diagram step by step. This process begins with the running process. All this stage, the CPU is actively executing one process. After a first short period, an interrupt occurs. This interrupt may be because of time quantum expiry, input output request, higher priority process arrival, hardware interrupt. Once an interrupt occurs, the operating system immediately stop the running process. However, before stopping its completely, the operating system save its current context into the process control block. This is an extremely important step because without saving the context, the process would lose all its progress. After saving the context, the CPU scheduler check the ready queue. It select another process that is waiting for execution. The operating system that restored the context of the selected progress from its PCB. Finally, the CPU resumes execution from exactly the same instruction where the process has stopped previously. Let's understand this using a classroom example. Suppose your teacher is checking the notebook of the student. She checks student's A's notebook for 5 minutes. Then she stops and starts checking student's B's notebook. Before moving to student B, she places a bookmark in student A's notebook. Later, when she returns to student A, she opens the notebook exactly from the bookmark page. That bookmarks works exactly like the process control block. It remembers where the work was stopped. This flow continuously repeatedly throughout the lifetime of the operating system. Therefore, the diagram summarizes the entire context switching process in a simple visual form. Now that we know how context switching works, let's understand the two important components responsible for the process, the CPU scheduler and the dispatcher. So we can move the next slide. CPU scheduler and dispatcher. Now let's discuss two very important components involved in context switching. These are CPU scheduler and the dispatcher. Also, both work together, their responsibility and different. Let's first understand the CPU scheduler. The CPU scheduler is the responsible for the deciding which process would get the CPU next. Imagine a railway station, many passengers are waiting to board the train. The station master decide which train will leave the first according to schedule. Similarly, many processes wait inside the ready queue. The CPU scheduler decide which process would run next. The scheduler make this decision based on different scheduling algorithms such as first come first served, shortage of first, priority scheduling, and round robin. After the scheduler select the process, the next component start working. This component is called dispatcher. The dispatcher job is actually give control of the CPU to the selected process. In simple word, scheduler decide, dispatcher execution the decision. The dispatcher performs several important tasks. First, it's restore the context of the selected process from that PCB. Next, it switches the CPU from old process to the next one. Finally, it transforms CPU's control all the execution can continue. Let's understand this what in a real life example. Imagine a cricket match. The coach decide which batsman should go to the crease next. The coach is similar to the CPU scheduler. The umpire then officially allow the batsman to enter the field and start playing. The umpire is similar to the dispatcher. So the scheduler chosen the process while the dispatcher make the switch happen. Both components are essential for switching context switching. Without the scheduler, the operating system would not know which process should next run. Without the dispatcher, the selector process would never actually receive the CPU. Together, they ensure fair CPU allocation, smooth multitasking, and efficient system performance. Now that we understand the scheduler and dispatcher, let's move to the practical example of context switching to see how everything works together in real life. This slide bring your we can move to the next slide. So this is the example of context switching. Now, suppose I switch on my laptop in the morning. First, I open Google Chrome to search for study material. At the same time, I open Microsoft Word to prepare my assignment. In the background, Spotify is playing music and Windows is downloading system updates. Now, think what a moment. What they can done, how my CPU execute all these applications at exactly in the same time. If it has only one processing core, the answer is no. The CPU can execute only one process at the particular instant. So how all these applications appear to be running together? This is where context switching come to the action. Initially, the CPU start executing Google Chrome. Chrome receive a small amount of CPU time called the time quantum. During the period, Chrome leads websites, processes user input and displays web pages. As soon as time quantum expires, the operating system interrupt Chrome. Before stopping Chrome, the operating system save all the Chrome current information such as program counter, CPU register, stack pointer, and process state. Inside Chrome process control bank, now the CPU become available for the another process. The CPU scheduler check the ready queue and select Microsoft Word. The dispatcher restored Word save context from its PCB. Immediately, Microsoft Word continue exactly from where it had stopped earlier. After a few milliseconds, Word's time quantum also expires. Again, the operating system save Word context. Next, Spotify gets CPU time. Spotify processes the audio data and continue playing music smoothly. Later, Windows Update receives CPU time and continue downloading files. This switching continues thousands of times every second. Because these switches happen so quickly, we never feel that one application is stopped while another start. Instead, we feel all applications are working simultaneously. This is actually all illusion created by the operating system through context switching. Without context switching, we would have to complete close Google Chrome where before opening Microsoft Word, we would have to stop Spotify before downloading any files. Modern multitasking would simply. Therefore, context switching makes our computer fast, responsive, and capable of handling multiple applications efficiently. So, this practical example clearly demonstrates how the operating system shares CPU time among multiple processes while maintaining smooth execution. Now that we understand its practical implementation, let's discuss the advantage of context switching. So the next we can move our next slide. Context advantage of context switching. Now let's discuss the advantage of context switching. Context switching is one of the most important feature of modern operating system because it provides several benefits that improve both system performance and user experience. The first advantage is multitasking. This is the probably the biggest benefit. Because of context switching, multiple applications appear to run simultaneously. For example, while preparing a presentation, we can listen to music, download it file, browse the internet, and chat with friends, all without closing any application. The second advantage is better CPU utilization. Sometimes a process waits for an input-output operation such as reading data from a hard disk or receiving information from the internet. Instead of allowing the CPU to remain idle during the waiting period, the operation system switches to another ready responses. As the result, the CPU remains busy most of the time, increasing overall efficiency. The third advantage is improved responsiveness. Interactive applications such as web browser, video calls, online games, and media players respond quickly because they receive CPU time regularly. Without context switching, user would experience long delays whenever multiple applications were running. Another important example is fair CPU allocation. The operation system ensure that every process receive an opportunity to execute. So single application can occupy the CPU identically. This creates fairness among all running process. Context switching also support real-time application. Critical applications such as medical monitoring system, banking service, air traffic control systems, and industrial automation require this. The operating system can quickly switch these high priority processes whenever necessary. Finally, context switching is increased overall efficiency of modern operating system. It allows better response management, smoother multitasking, improved user experience, and higher productivity. In short, without context switching, today's computer, smartphone, and several would not be able to perform multiple tasks efficiently. However, like every technology, context switching also had a certain disadvantage. Let's discuss the next slide. So we can discuss the next slide, disadvantage of context switching. Although context switching provides many disadvantages, it also have a same limitation. The first disadvantage is context switching overhead. Whenever the system switches from one process to another, it has to save the current process context and restore the next process context. During this time, the CPU is not performing any useful computation. Instead, it is busy performing administrative work. This extra work is called a context switching overhead. If context switching happen too frequently, the overhead increases and system perform may decreases. The second disadvantage is perform reduction. Every context switches consume a small amount of CPU time. Individually, the delay is very small. However, if thousands of context switches occurs every second, the total overhead becomes significant. As a result, the CPU spends more time switching process than executing useful instruction. Another disadvantage is performance loss. Modern CPU use high-speed memory, cache memory to improve execution speed. When a new process start executing the cache to change, the useful data of the previous process may be removed from the cache. What the process run again, it was the reload, so it required the data into a cache, causing additional delays. Context switching also increase the operating system completely. The operating system must carefully maintain process control blocks, scheduling algorithm, memory management, synchronization mechanism, and interrupt holding. The designing such as operating system requires significantly effort and advanced algorithm. Finally, execution context switching can reduce overall system efficiency if the operating system spend too much time switching between process. Users may experience slower application process. Therefore, operating system try to balance context switching carefully. They perform uh, enough context switches to support multitasking, but they avoid unnecessary switching that wastes CPU time. So, although context switching introduce some overhead, its advantage greatly outweighs its disadvantage. It remains one of the most essential mechanisms that make modern multitasking operation system. Now that we have discussed both the advantage and disadvantage, let's move to the final section of our presentation where we will summarize the topic and conclude our discussion. So our next slide is real life application of context switching. Now that we understand the complete concept of context switching, let's discuss where it is in real life. Many students think that context switching is a theoretical concept through an operating system. However, the truth that we experience it every day without even some realizing it. The first and most common application is smartphone. Whenever we use our mobile phones, we often keep multiple applications open at the same time. For example, we may be listening the music on Spotify, chatting on WhatsApp, browsing Instagram, downloading files, and receiving notifications from Gmail all at once. Although it feels like all these applications are running simultaneously, the operating system is actually perform context switching continuously. The CPU gives each application a small amount of process time and repeatedly switches between them. Since the switching happened it just a few milliseconds, user never noticed it. The second application is web browser. Suppose we open Google Chrome with 10 or 15 tabs. Some tab are playing YouTube videos, another tab is downloading a PDF, another is loading a website, while one tab is running an online coding platform. All these browser tabs require CPU time. The operating system perform context switching so that every tab receive a fair share of the processor. This creates the illusion that every tab is work simultaneously. Another important application is online gaming. Modern games perform many activities at the same time. The process graphics, detect keyboard, mouse input, play background music, communicate and with online server and calculate game physics. These tasks are handled by different processes and threads. Context switch allow the operating system to manage all these activities efficiently, provide a smooth game experience without a noticeable delays. The next application is banking system. Bank handle thousands of customer transaction every second. People withdraw money from ATMs, transfer fund through mobile banking, making online payments and check account balance simultaneously. The operation system continuous switches between different banking processes to ensure that every transaction is processed quickly and accurately. Another important example is cloud computing and data centers. Companies like Google, Microsoft, and Amazon run thousands of applications on powerful servers. Millions of users access this service simultaneously. Context switching enables servers to efficient share CPU resources among different users and applications. Finally, context switching is widely used in hospital, air traffic control system, industrial automation, and embedded system where quick response and efficient multitasking are essential. Therefore, context switching is not just a classroom topic; it is an core technology that enables modern computer, smartphones, cloud service, and real-time system to function efficiently. Now that we have seen its practical application, let's summarize everything we learned today. So we can move to the next slide. So finally, we explored several real-time applications including smartphone, web browser, online games. So understanding context switching help our appreciate how operating system manage multiple applications smoothly while ensuring fairness, efficiency, and responsiveness. So we can conclude our presentation. So thank you for your kind attention. This brings me to end of the presentation. Thank you everyone for your valuable time and patient listening. I hope this presentation has helped you understand the concept of context switching and how the operating system manages multiple processing efficiently. Context switching may happen in just a few milliseconds, but it plays a vital role in making modern operating system fast, responsive, and capable of multitasking. I sincerely thank my respected teachers and all my classmates for giving me this opportunity to present me this topic. If anyone has any question or would I like to explain any concept again, I would be happy to answer. Thank you and have a great day. So we can so thank you.